It's time we started solving differential equations. This is the third lecture of the term, and I have yet to solve a single differential equation in this class. Well, that will be rectified from now till the end of the term. So once you learn separation of variables, which is the most elementary method there is, I think the single most important equation is the one that's called the first order linear equation, both because it occurs frequently in models, because it's solvable, and I think that's enough. If you drop the course after today, you'll still have learned the two important methods: separation of variables and first order linear equations. So what does such an equation look like? Well, I'll write it in, there are several ways of writing it, but I think the most basic is this. I'm going to use x as the independent variable because that's what your book does, but in the applications it's often time, that's the independent variable, and I'll try to give you examples which show that. So the equation looks like this. Some function of x times y prime plus some other function of x times y is equal to yet another function of x. Obviously, the x doesn't have the same status here that y does, so y is extremely limited how it can appear in the equation, but x can be pretty much arbitrary in those places. So that's the equation we're talking about, and I'll put it up. This is the first version of it, and we'll call them purple. Now, why is that called a linear equation? The word linear is a very heavily used word in mathematics, science, and engineering. For the moment, the best simple answer is because it's linear in y and y prime, the variables y and y prime. Well, y prime is not a variable. Well, you'll learn in a certain sense it helps to think of it as one, not right now perhaps, but think of it as linear by the most closely analogous thing would be the equation, a linear equation that looked like a real linear equation, the kind you studied in high school, which would look like this. It would have two variables and, I guess, constant coefficients equal c. Now, that's a linear equation, and that's the sense in which this is linear. It's linear in y prime and y, which are the analogs of the variables y1 and y2. A little bit of terminology. If c is equal to 0, it's called homogeneous. The same way this equation is called homogeneous, as you know from 1802, if the right-hand side is 0. So c of x I should write here, but I won't. That's called homogeneous. Now, this is a common form for the equation, but it's not what's called standard form. The standard form for the equation, and since this is going to be a prime course of confusion, which is probably completely correct, but a prime source of confusion is what I meant. The standard linear form, and I'll underline linear, is the first coefficient of y prime is taken to be 1. So if I divide, you can always convert that to a standard form by simply dividing through by it. And if I do that, the equation will look like y prime plus. Now, it's common to not call it b anymore, the coefficient, because it's really b over a. And therefore, it's common to adopt yet a new letter for it. And the standard one that many people use is p. How about the right-hand side? We need a new letter for that, too. It's c over a, but we'll call it q. So when I talk about the standard linear form for a linear first-order equation, it's absolutely that I'm talking about. Now, you immediately see there's a potential for confusion here, because what did I call the standard form for a first-order equation? So I'm going to say not this. The standard first-order form what would that be? Well, it would be y prime equals and everything else on the left-hand side. So it would be y prime, and now if I turn this into the standard first-order form, it would be negative p of x, y, plus q of x, but of course nobody would write negative p of x, so now I explicitly want to say that this is a form which I will never use for this equation, although half the books in the world do. In short, this poor little first-order equation belongs to two ethnic groups. It's both a first-order equation, and therefore its standard form should be written this way, but it's also a linear equation, and therefore its standard form should be used this way. Well, it has to decide, and I have decided for it. It is above all a linear equation, not just a first-order equation, and in this course, this will always be the standard form. Now, well, what on earth is the difference? Oh, if you don't do it that way, the difference is entirely in the sign of p, but if you get the sign of p wrong in the answers, it's just disaster from that point on. A trivial little change of sign in the answer produces solutions and functions which have totally different behavior, and you're going to be really lost in this course. So maybe I should draw a line through it to indicate, please don't pay any attention to this whatsoever. Except that we're not going to do that. Okay? Well, what's so important about this equation? Well, number one, it can always be solved. That's a very, very big thing in differential equations. But it's also the equation which arises in a variety of models. Now, I'm just going to list a few of them. All of them, I think, you will meet in either in part one or part two of problem sets over these first couple of problem sets, or second and third maybe. But of them, I'm going to put at the very top of the list what I'll call here, I'll give it two names, the temperature diffusion model. Well, I'm sorry, it would be better to call it temperature concentration by analogy. Temperature concentration model. There's the mixing model, which is hardly less important. In other words, it's almost as important. You have that on your problem set. And then there are other slightly less important models. There's the model of radioactive decay. There's a model of a bank interest, bank account. Various motion models. You know, Newton's law type problems, if you can figure out a way of getting rid of the second derivative. Some motion problems. A classic example is the motion of a rocket being fired off, et cetera, et cetera, et cetera. Now, today I have to pick a model, and the one I'm going to pick is this temperature concentration model. So this is going to be today's model. Tomorrow's model in the recitation, I'm asking the recitations to, among other things, make sure they do a mixing problem. To show you how to do it, and B, because it's on the problem set, so that's not a good reason, but it's not a bad one. The others are either in part 1 or we'll take them up later in the term. This is not going to be the only lecture on the linear equation. There'll be another one next week of equal importance, but we can't do everything today. So let's talk about the temperature concentration model, except I'm going to change its name to the conduction diffusion model. I'll put conduction over there and diffusion over here, let's say. Since, as you'll see, the similarities, or they're practically the same model, all that's changed from one to the other is the name of the ideas. In one case you call it temperature, and the other case you call it concentration, but the actual mathematics isn't identical. But so let's begin with conduction. All right, here's I need a simple physical situation that I'm modeling. So imagine a tank of some liquid. Water will do as well as anything. And in the inside is suspended somehow is a chamber. A metal cube will do. And let's suppose that its walls are partly insulated. Not so much that no heat can get through. There is no such thing as perfect insulation anyway, except maybe a perfect vacuum. Now, inside, so here on the outside is liquid. Okay. On the inside is what I'm interested in is the temperature of this thing. I'll call that T. Now, that's different from the temperature of the external water bath, so I'll call that T sub E. T for temperature, measured in Celsius, let's say, for the sake of definiteness. But this is the external temperature, so I'll indicate it with an E. Now, what is the model? Well, in other words, how do I set up a differential equation to model this situation? Well, it's based on a physical law, which I think you know. You've had simple examples like this. The so-called Newton's law of cooling. Which says that the rate of change, the temperature, the heat goes from the outside to the inside by conduction only. Heat, of course, can travel in various ways: by convection, by conduction, as here, or by radiation are the three most common. Of these, I only want one, namely transmission of heat by conduction. And that's the way it's probably a little better to call it the conduction model rather than the temperature model, which might be involve other ways for the heat to be traveling. So dt, the independent variable, is not going to be x as it was over there. It's going to be t for time. So maybe I should write that down. T equals time. Capital T equals temperature in degrees Celsius, so you put in the degrees Celsius if you want. So it's proportional to the temperature difference between these two. Now, how shall I write the difference? Write it this way, because if you don't, you'll be in trouble. Now, why do I write it that way? Well, I write it that way because I want this constant to be positive, a positive constant. In general, any constants or parameters which are physical, have some physical significance, one always wants to arrange the equation so that they're positive numbers, the way people normally think of these things. This is called the conductivity. The conductivity of what? Well, I don't know, of the system, of the situation. The conductivity of the wall, or if the metal were just by itself, it would, at any rate, it's a constant. It's thought of as a constant. And why positive? Well, because if the external temperature is bigger than the internal temperature, I expect T to rise, the internal temperature to rise. That means dt, its slope should be positive. So in other words, if TE is bigger than T, I expect this number to be positive. And that tells you that K must be a positive constant. If I had turned it the other way, expressed the difference in the reverse order, K would then be negative, have to be negative in order that this turn out to be positive in that situation I described. And since nobody wants negative values of K, you have to write the equation in this form rather than the other way around. So there's our differential equation. It will probably have an initial condition, so it could be the temperature at the starting time should be some given number T0. But the condition could be given in other ways. One could ask, what's the temperature as time goes to infinity, for example? There are different ways of giving that initial condition. Okay, that's the conduction model. What would the diffusion model be? The diffusion model mathematically would be word for word the same. The only difference is that now what I imagine is, I'll draw the picture the same way, except now I'm going to label the inside not with a T but with a C. C for concentration. It's in an external water bath, let's say. So there's an external concentration. And what I'm talking about is some chemical, let's say salt will do as well as anything. So C is equal to salt concentration inside, and CE would be the salt concentration outside. Outside in the water bath. Now, I imagine some mechanism. So this is a salt solution, that's a salt solution, and I imagine some mechanism by which the salt can diffuse. It's a diffusion model now. Diffuse from here into there, or possibly out the other way, and that's usually done by vaguely referring to that the outside is a semi-permeable membrane. Semi-permeable so that the salt will have a little hard time getting through, but permeable so that it won't be blocked completely. So there's a membrane, you write the semi-permeable membrane outside. Outside the inside. Well, I give up. You know, not membrane somewhere. Sorry. Membrane wall. How's that? Now, what's the equation? Well, the equation's the same, except it's called the diffusion equation. I don't think Newton got his name on this. The diffusion equation says that the rate at which the salt diffuses across the membrane, which is the same up to a constant as the rate at which the concentration inside changes, is some constant, usually called K still. Okay. Do I contradict? Yeah, okay. Let's keep calling it K1. Now it's different. Times CE minus C. And for the same reason as before, if the external concentration is bigger than the internal concentration, we expect salt to flow in. That will make C rise. It will make this positive, and therefore we want K to be positive, just K1 to be positive for the same reason it had to be positive before. So in each case, the model that I'm talking about is the differential equation. So maybe I should let's make that clear. Or I would say that this first order differential equation models this physical situation, and the same thing is true on the other side over here. This is the diffusion equation, and this is the conduction equation. Now, if you were in any doubt about the power of differential equations, the point is, when I talk about this thing, I don't have to say which of these I'm following. I'll use neutral variables like y and x to solve these equations, but clearly with a single stroke, I will be handling both situations together, and that's the power of the method. Now, you obviously must be wondering, look, hey, these look very, very special. He said he was going to talk about the general first-order equation, but these look rather special to me. Well, not too special. How shall we write it? Suppose I'll write it let's take the temperature equation just to have something definite. Notice that it's in a form corresponding to Newton's law, but it is not in the standard linear form. Let's put it in standard linear form, so at least you can see that it's a linear equation. So if I put it in standard form, it's going to look like dt dt, d little t, plus kt is equal to k times te. Now compare that with the way the general equation is supposed to look, that yellow box over there, the standard linear form. How are they going to compare? Well, this is a pretty general function. This is a general function of t, because, you know, I can make the external temperature, I can suppose it behaves in any way I like. Steadily rising, decaying exponentially, maybe oscillating back and forth for some reason. The only way in which it's not general is that this k is a constant. So I will ask you to be generous. Let's imagine the conductivity is changing over time. So this is usually constant, but there's no law which says it has to be. How could a conductivity change over time? Well, we could suppose, for example, that this wall was made of slowly congealing jello, for instance. You know, it starts out as liquid, then it gets solid, and jello doesn't transmit heat, I believe, quite as well as liquid does, as a liquid would. Is jello a solid or a liquid? I don't know. Let's forget about that. So with this understanding, so let's say not necessarily here, but not necessarily, I can think of this, therefore, by allowing k to vary with time and the external temperature to vary with time. I can think of it as a general linear equation. So these models are not special, they're fairly general. Well, I did promise you I would solve an equation, and in this lecture I still have not solved any equations. Okay, time to stop temporizing and solve. So I'm going to, in order not to play favorites with these two models, I'll go back to, and to get you used to thinking of new variables all the time, that is, you know, being eclectic, switching from one variable to another according to which particular lecture you happen to be sitting in. So let's take our equation in the form y prime plus p of xy, the general form, using the old variables equals q of x. Solve me. Well, there are different ways of describing the solution process. No matter how you do it, it amounts to the same amount of work. And there's always a trick involved in each one of them, since you can't suppress a trick by doing the problem some other way. The way I'm going to do it, I think, is the best. That's why I'm giving it to you. It's the easiest to remember, leads to the least work, but I have colleagues who would fight with me on that point. So since they're not here to fight with me, I am free to do whatever I like. One of the main reasons is that of doing it the way I'm going to do is because I want you to get one more word into your consciousness, and that's the word, two words, integrating factor. I'm going to solve this equation by finding an integrating factor of the form u of x. What's an integrating factor? Well, I'll show you, not by writing an elaborate definition on the board, but showing you what its function is. It's a certain function u of x. I don't know what it is, but here's what I want it to do. I want to multiply, I'm going to drop the x's